go for the second lecture, which is by Professor Ranjith Thapa. He is Professor and Dean Research at SRM University AP. I'll just go through this CV, which is a short CV, but it will take a few minutes just for the sake of the audience who would like to know about his accomplishments. Professor Ranjit Thapa is designated as Dean Research of SRM University AP and full professor in the Department of Physics, SRM University. Professor Ranjit is actively involved in fostering thriving research ecosystem at SRM University, providing valuable insights on maintaining a harmonious balance between academics and research within the university system. He has researched computational material science technologies for past 14 years. You can see the strength coming from the computational material science technologies. He received the Young Associated Award in 2016 from the Indian Academy of Science, Bangalore, for his outstanding research in computational material science. That's the real strength. He was also chosen for BRNS Young Scientist Research Award for the year 2018. He was awarded the Best Researchers Award 2020 by SRM University. He received the Outstanding Teachers Award in 2023, just this year. He has published more than 160 research articles in highly reputed international journals. His current H index is 35 with total citation of more than 4,200. Currently, he is developing a materials database under the funded projects. He has mentored 8 PhD students to date. In 2016, under his leadership, SRM Institute of Science and Technology established a high-performance computer center on the Chennai campus. Similarly, in 2022, he was pivotal in establishing a high-performance computer center at SRM University. Professor Ranjit's research endeavors primarily revolve around the application of first principle theory in investigation. Some of the notable contributions include development of electronic and structural descriptor, which is nothing but a simple graphical construction for identifying optimal catalysts for ENRR and CO2, I think. I'm sorry for that. The findings from these studies have been published in esteemed journals such as Carbon, Chemical Science, PNS, Advanced Functional Materials, ACS Nano, Nano Micro Letters. You can just see the list of journals and the wide variety which he has published that show the strength in the material science computational technologies. I think with this brief
it's a long, I
which
think
he
they
has given,
collected from
I
the
had to do-
website. Whatever I
to
have
do
given,
justice.
it was very short,
Yeah.
maybe 5 lines. Thank you, Professor. And let's start the presentation. I will, because we have less time, I will put the timer also. Yeah. So, so today I'm going to talk and on hybrid anode materials, and of course using computational technique what we have done in the last 4 or 5, 6 years. And another thing is that limitation of lithium de-intercalation in cathode. So these two phenomena I'm going to explain in next 20-25 minutes. So let me first show that where I belongs to. Actually, SRM is also in Chennai, which is SRM Institute of Technology, Science and Technology. And currently I belongs to SRM University AP, which is under State Act University. And we are a 6 years young university, and which is located in between Vijayawada and Guntur. So this is the train which I booked, and I was really waiting to take this train study night, but I have decided not to come because there was very ambiguity about the train journey, and you can see still the train have not reached Chennai. So I could have been lost both online and offline if I would have been taken this train. And as I belongs to this place and study in the same time evening, the cyclone was heading towards this position, which is almost 50 kilometers from my current location. So now it's clear, everything is fine. And so hope I can come again any next time for in IIT Chennai.
Yeah, you're most welcome.
Yeah. So this is the group actually which we focus also on the descriptor, which is on quantum mechanics machine learning approach. And because this is one of the heart of our group, we started around 2017 this concept of descriptor theory. And you can see, and then we have really gone through a long journey of 6 years, and we have really proved, or we can say that we have discovered a descriptor which can also predict and also validate the experimental result, or we can say we can predict and experiment can use that result directly. And the DFT calculation we have reduced is almost 20 to 30 times by using this approach. So this is the journey from 18 to 23 which I am showing here as one of another area where I am working. And so this is related to today's topic, where I'm focusing more on the materials of battery materials. So this is the basic principle which I don't have to explain to this community. Of course, we are working on particularly material. There are various components of the battery, but we focus on the basic understanding of the materials and how the theoretical parameters we can identify which can match with the experimentalist results or experimental result, and then we can guide them also. So overall, for any selection of battery materials, either it will be lithium ion battery or it will be sodium ion battery, we always see the potential. If it is a cathode or anode, we decide based on the where it is. So it is a cathode, it is an anode. Of course, the nomenclature is different with respect to the usual battery because of the movement of the ion is considered as a basic parameters to define the anode or cathode. So here we are in the cathode, they are almost in the 4 range of volt, and in the anode it is around 0.4, which is graphite, and other anodes are also there. The difference between this is our cell potential. So higher this difference, we will get better and better cell potential. We also will have 1.5 volt of battery, but recently lithium ion batteries are almost 3.4, 3.5 volt. So this is the window which define the batteries voltage. And for sodium, of course, the voltage is not so high. It is also equivalent to you can see equivalent to your lithium, but because of the abundancy of the sodium, a lot of research is going on to move towards the sodium and battery. So what theoretical workflow we follows, actually we are considering different model structure, and then we use to calculate density of states and band structure and different parameters, and then we calculate using our total energy, we calculate open circuit voltage, and we can calculate specific capacity, which is a theoretical specific capacity. We calculate volume expansion and we calculate formation energy. This is about the density functional theory, what we can do in our group. So how to calculate volume expansion, I have just given for the student audience that you can easily calculate volume expansion by intercalation or de-intercalation process and calculate the volume, and we can easily find out using our theoretical point of view. Open circuit voltage, which is very much equivalent to your potential, which I have shown in the previous slides, we can also calculate by finding the Gibbs free energy and also the concentration of how many lithium we are taking out, and then Faraday constant. And by using this method, we can easily calculate the open circuit voltage. And another parameter, which is the formation energy, because how much you are putting the lithium or how much you are extracting the lithium, based on that, what is your stability of the materials, it defined by the formation energy, which we can use this formula to calculate. So this is the story which I am going to tell in a very I will say in an abstract way. So I think in carbon we have published in 2021 a hybrid structure of silicon and carbon, and in 2022 it's C2N and again carbon, and recently borophosphine and other things are there. Graphite is there, which we have published in Journal of Power Source. What I'm overall is telling is that there are the single materials like carbon or silicons and other things are already in the market, but the generation which is coming, or very soon it is very soon in the market, is that the anode will be mixed anode. And of course many people are trying, but you cannot change the industry suddenly from the graphite to some other material, because industry now will not allow you. So you have to find a material which will be matched with the graphite and enhance the specific capacity from 332 to 500 specific capacity without changing much in the OCV or your overall volume expansion. So this is a challenge. So we have identified the mechanism and understanding how you can do it, how you should approach another thing. So we have reported that there are few materials which we can do, and then we have given the theoretical understanding why this is working like that. So these are the previous works from the literature, where you can see that C2N, C3N is a mixed anode material. So this is the, I will say this is the decade of the mixed anode material, which is going to come into the market in your laptop and everywhere very soon. That the anode will be no more only graphite, it will be included with any other secondary material. Of course, silicon and anode is already in the market, but it will be now mixed. So C2N, C3N new anode materials, which is reported in advanced material by both theory and experimental group. So you can see this, and then you have C3N phosphorine heterostructure, a promising anode material in lithium and battery. It is the same time when we are also doing the work in the direction of this anode material. And then capping black phosphorine by HBN. So it's also a mixed type where they have proved from our Indian IACS lab that this also could be a better anode material for the lithium and batteries and sodium and battery. So again, when we are doing for such a lithium, we have to also understand the diffusion mechanism. So there are a lot of studies on the diffusion, that how it will be going is because the diffusion kinetics in the battery for the anode, it is around 0.3 electron volt, the barrier when one side to another side lithium is moving, because during your charging and discharging inside the lithium movement is very important. So that type of study also we can do using our density functional theory. So these are the few examples where they have also shown the diffusion, and which are very important in terms of experimental point of view, because such very precise study is very very limited in terms of experimental point of view. So one work I will go in detail, and the second work also I will try to finish fast. So this is the work which we have considered as a silicon and graphene or graphite mixed up, a heterostructure, and how we have shown that if you increase the content of silicon or increase the content of carbon layer, how the specific capacity is changing and why it is changing. So we have taken different models of and one more important thing is that when we are doing for any anode material calculations, it all is in the bulk features. They are not in the nano range or other things. If you are doing any surface calculations and you are putting your lithium on the surface, and then you are telling that it has increased the specific capacity, that means it's a wrong calculation. You always have to take the bulk overall to find the actual specific capacity. So that's why you can see the overall in the C axis, this is the closed one, so it looks like it's a bulk. So so this is the overall electronic structure you can see here. So silicon is of course and silicon and carbon layer will be here. So you can see here the most of the two concept is there, is that carbon layer is helping for electronic conductivity, means the electron will move very easily, and whereas the silicon will help you to increase the specific capacity. So through the density of state, you can see the more number of electron due to the pi electron or pi orbitals of your of your carbon, whereas the pi orbiter of silicon is more localized compared to the carbon is delocalized. So in that case, the more electron will flow using the layer of carbon, whereas the lithium movement or any stability or more lithium will be there due to the presence of localized pi of the silicon. So this is the overall we have explained in that work. And then we calculated, as we said, that we can calculate open circuit voltage, formation energy, and volume expansion. And you can see that we have calculated all these things, and it is really coming negative for formation energy. And OCV, you can see this is the graphite. So overall, it is 0.4, which is the result. And when we included the silicon, of course, we can increase up to 2 the specific capacity, but the OCV is increasing to around 0.8 volt. So that means if you increase more and more silicon, or how much you need to give the silicon, so that your OCV will be maintained, and your overall specific capacity you can increase from suppose 1 to 2 lithium per unit cell. So that means 300 to 600 milliampere per hour per gram. So from there you can change from 300 to 600, but your OCV will also increase in that case. So, and the volume expansion looks very good even if we put the silicon. And the main thing is that it is not about the putting of the electron, it is also a removing of the electron. So what will happen when you are putting the cycle? Is it really form a stable and other things? And we found that yes, the structure is stable even after 20 cycles. So this is the first time we have shown that theoretically also we can show the cyclic process of the lithium intercalation and de-intercalation. So after that, what will be your diffusion? How the lithium should go inside? So in that case, you can see easily that if lithium is inside the carbon, the diffusion energy barrier is around 0.3. But if it is going in between silicon and carbon, the diffusion increase to 0.5 or 0.6 electron volt. So that means you need to have to quantify what is the reason, and all the reason is because of your localized pi of silicon and delocalized pi of carbon. And we have really matched all these results, and we have shown how much percentage of your silicon should be there, so that it can be easy for you to maintain such heterostructure for your anode material. And of course, today or tomorrow, silicon graphite based anode is coming into the market very soon, and many companies are working towards this in the last 5 years. So this is the overall conclusion of this work in a very short. So you can easily change the specific capacity. Your volume expansion will also change, your OCV also change. So which one you want more, and how you can you want to make it optimized, that is the important message we have given from this work. Similarly, so we have also gone to any other works which is our C2N, C3N plus graphite. And when we have, again, I have not changed the graphite as a base material, because as I said, the graphite will not change in the even next 10 years or 10 to 20 years in your things. So you have to find a way how you can use the graphite with some other material to increase the specific capacity. So C3N and graphene, we have again shown the same way, and we have shown that the fundamentally that if you just change the plane directions with respect to each other, it can easily change from semiconducting to metallic behavior. And for your anode, you need metallic behavior anode material, because you need electrons to move to the circuit back during your intercalation or de-intercalation process. So you have to find out which will be the more and which is the main configuration. And then we have done all the same calculations what we have done in the previous work, and then we have identified that how the two layers charge density difference or the localized delocalization, because graphene is mostly delocalized, but wherever C3N have a nitrogen bond and nitrogen have a your localized, I will say that lone pair electron is there, so which will really create sometimes repulsion or attraction depending upon type of molecule which it is interacting. So in this way we have formed different type of anode materials, and again we have calculated OCV, and you can see that OCV you can really make it very well, particularly for the this red one or this blue one, where and even for the black one where C3N monolayer and one graphene layer. Of course, it is a theoretical point of view. It is like you can say experimentalist means 50-50. If there is layer by layer interactions, then your OCV will be within the range of 0.4. So which is the demand of the industry, because you should not increase OCV more than 0.6, 0.7 like that. And formation energy is quite well for this black curve, and your volume expansion is also very low. So overall, it is showing that this also could be one of the materials which experimentalists are trying or could try more in the lab. So diffusion kinetics, again, we have done it, and we have shown that diffusion is changing from 0.5 to 0.3 in different layers of C3N or graphene. So I'm going to just discuss the understanding of the cathode material, which is also we have expertise and we can do it. And what we have done in that work, of course, in collaboration with Professor Ranjit Nanda, he is also from Department of Physics, IIT Madras. We want to understand that in the cathode, if you see, the main thing is that even there is a 3 lithium, all 3 lithium don't come out during the de-intercalation process. What is the reason behind that? Can we increase the number of lithium to be come out from that, so that it can enhance the specific capacity of the cathode material? Because cathode material specific capacity is low, which is more challenge. It's around 150, 160, around that. If we can take this to the 200 to that level or 210 level, that will have a very huge market demand, such cathode material. So why it is not happening? Who is stopping that? That was one of the approach which we want to address theoretically. And there are a lot of works happen in the we have taken one of the example is LVP. This is the one of the material which is very well known. So we have taken this, and then we have understand why it is not happening. So this is just an introduction of the same work, and then we have seen that this lithium vanadium phosphate LVP have 3 type of lithium: L1, L2, and L3. Now that means this 3 lithium, because of its coordination, because of its environment, because of its different nature of tetrahedral bonding, they behave differently, or how they will behave if I put any other foreign element. That is the concept. And who is the lithium who is having the obstacle to go for 3 lithium de-intercalation? So this was the concept, and then we have addressed this. That's this issue. Before going into that, we want to understand that how the band structure or electronic structure is changing when we are bringing out all the lithium. So we have seen that lithium 3, when we bring out all the lithium from the vanadium, which is we are doing only theoretically, experimentally only 1.8 electron can come out, sorry, 1.8 lithium can come out during the de-intercalation process. But we want to see if we bring out all the lithium, then it become more metallics, and that is the reason why these structures are changing, and from semiconductor towards metallic it is changing. From lithium vanadium phosphate to vanadium phosphate during the de-intercalation process. So that means lithiums have some roles, and oxygen have also some roles, vanadium also have some role, that we have to understand or address to the experimentalist more very clearly what they should do in that way. Then when we have done in that way, then what we found out, you can see that lithium 1, lithium 2, and lithium 3. So the formation energy per vacancy is different for different lithium. So that means if I change this formation energy, means if when I'm bringing out one lithium, I need more energy for one lithium, I need less energy for another lithium. So can we do in such a way, and when we bring out all these three lithium, structure become unstable, very unstable, because you can see this black curve, this after putting some lithium 1.8, it goes in the positive because structure become unstable. So we have put a boron as one of the component in terms of vanadium. Then we have shown that if you see the structure is stable, even you put more than 2 lithium per that compound, lithium vanadium phosphates, one compound formula, then it is more stable. So why it is happening? Then we shows that it is happening because of the vacancy energy. So we are dealing with the vacancy energy and also the oxidation state of the vanadium. So if we change that by doping with the boron and we correlate that, then you can easily increase the lithium extractions from the cathode. So our main is we have to extract more lithium from the cathode and give it to the anode. So this was one of the idea which we have given, that you should approach in that direction. You should add such element which will change the vacancy energy, and then you can have a better cathode material. So this is again diffusion, because cathode material also need the diffusion. So we have studied it. And so important finding I will say for the cathode is lithium vacancy energy decreases towards negative by boron, and which helps to be more lithium de-intercalations, and we can achieve around 205, which is theoretically, of course, a specific capacity into that. So this is the way how we have done the work and address. And what is our planning of this is the present thing which we can do we in our group, but maybe in 2 to 3 years we have now have a center for computational and integrative science. And if we can do such simulations in different scale, that means we can do molecular dynamics of the batteries material, we can do ACI ACI calculations with the molecular using the molecular dynamics, and then cell packing and other thing. So this is the ultimate goal of this Center for Computational and Integrated Science in India, if you can do it. So just before finishing, this is the two conference which this is the one conference which we are doing in February. Of course, IIT Madras, Nanda is also there with me. And this is the NSM supported workshop for students who can apply, and it is mostly free. Everything we are taking care. The student can come and learn from us how to design the computation for the electrocatalyst. And thank you. And these are my collaborator, Professor Umesh, Shobhana, Nanda, Ramendra, and Uttam. Yeah, thank you to all my funding agency and HPCC facility of SRM University AP. Thank you.
Good. Thank you, Professor Ranjith Thapa. We'll have quickly 1 or 2 questions. Okay, I don't think so there are any questions. So
Okay.
we again thank you once again.
Sorry, I have a question.
Please.
Is it okay? I'm Ken Watanabe from Kyushu University. Thank you for very, very interesting talk.
Yeah, please. Go ahead with your question.
So my question is very, very simple. So you can calculate the new anode material based on the oxide. Could you predict some candidate for the next generation oxide-based anode material?
Yeah, we can do. We can calculate. We can calculate. Yes, we can calculate anode material and predict it. But of course, based on some intuition, we can do till now. Because if you want to predict, then of course, machine learning we are not doing here. But yes, we can do it. We can predict if anyone have any type of composition there, then we can predict yes, it is a good or not, much more faster than experimentalist.
Other time, I have an interest about the thermal stability or reactivity with some solid electrolyte at high temperatures. So is it possible for you to include such parameter in machine learning?
Yes, that's what I'm telling that we can do, because whatever you have told, this parameter is about SEI, which is a solid electrolyte interface. And before that, we must need minimum 100 or 200 data point of same class of material. Okay, so if we have, or if any of the publication have such, or we can collect also of such class of material, have 100, 200, 300 data points, that we can predict which could be the better in that direction.
Okay, that's nice.
Yeah.
Thank you very much.
Yeah.
Okay. So if not, let's thank Professor Ranjit Thapa once again for a very enlightening lecture. Thank you. I leave it over to the coordinators.
Please join us to thank Professor Indrapal Singh for chairing this session. Thank you, sir.